a real experiment in the lab, it is never possible to recover 100% of the products of a chemical reaction. For instance, if a product is a gas, some of it may escape into the atmosphere and not be collected. If a product is a liquid, it may partially evaporate. Some liquid or solid product may also be lost when it is transferred from one container to another, or may spill or splatter in the course of the reaction. Once a reaction is performed in the lab, the mass of the product of interest can be measured, and this mass is referred to as the actual yield of that product. The actual yield is found separately for each product. As we have seen in the previous video, the molar ratio coefficients in a balanced chemical equation can be used to predict how much of each product should be formed if a given amount of reactants is used. We referred to this predicted amount of product as the theoretical yield. Although in the previous video we expressed the theoretical yield as the number of moles of a product that could be formed for a given amount of reactants, it is more common to express it as the mass of that product. If we know the number of moles of a product, to calculate its mass we simply need to multiply this number of moles by the molar mass of the product. Therefore, there is a unique one-to-one correspondence between the number of moles of a substance and the mass of that substance. In other words, if we know the number of moles of a substance, we can always find its mass, and vice versa. The actual yield, that is the mass of the product actually obtained in a chemical reaction, can be compared to the theoretical yield, that is the mass of the product that should have been obtained in the reaction if none of the product was lost. This comparison is most commonly performed by calculating the percent yield, which is defined as the actual yield expressed as a mass divided by the theoretical yield expressed as a mass and multiplied by 100%. The percent yield is the actual yield divided by the theoretical yield times 100%. The percent yield can never be greater than 100%, because if all atoms available to build the product were used up, we would only get as much product as the theoretical yield predicts, so there is no way to get any more product. If you perform a chemical reaction and find that the percent yield is greater than 100%, it means that the product has been contaminated. That is, there is something in addition to the product of interest in your container that shouldn't be there. If the percent yield is much smaller than 100%, it means that you are losing a significant amount of reactants or products in the process of your reaction. Increasing the percent yield of products is an important consideration when designing processes by which chemical reactions are carried out in the chemical industry. Let's perform a sample calculation of the percent yield. Consider the following balanced chemical equation. 2 solid sodium plus 2 liquid water forms 2 sodium hydroxide in aqueous solution plus hydrogen gas. Let's say that after 18.16 grams of sodium was placed in 50.0 grams of water, 0.258 grams of hydrogen gas was collected. We want to find the theoretical yield and percent yield of hydrogen gas. The molar ratio coefficients in the chemical equation tell us that we need to take as many atoms of sodium as we take molecules of water, a 2-to-2 ratio, which is the same as a 1-to-1 ratio, to completely use up both reactants. But what is the ratio between the numbers of sodium atoms and water molecules that we actually have available? To find out, we can convert the masses of sodium and water to the amounts of sodium and water, most conveniently expressed in the number of moles. To find the number of moles of sodium, we need to divide the mass of sodium, 8.16 grams, by the molar mass of sodium that we can find in the periodic table, 22.990 grams per mole. Dividing 18.16 grams by 22.990 grams per mole, we find that the amount of sodium is 0.355 moles, where we have taken the correct number of significant digits. To find the number of moles of water, we need to divide the mass of water, 50 grams, by the molar mass of water that can be calculated by taking twice the molar mass of hydrogen, 1.008 grams per mole, plus the molar mass of oxygen, 15.999 grams per mole, which adds up to a total of 18.015 grams per mole. Dividing 50.0 grams by 18.015 grams per mole, we find that the amount of water is 2.78 moles, where we have taken the correct number of significant digits. We said that the ratio of the amount of sodium to the amount of water should be 1:1 in order to use up both reactants completely. However, we actually have a lot more water, 2.78 moles, than we have sodium, 0.355 moles, meaning that we don't have enough sodium to completely use up all water, so sodium is the limiting reactant. At this point, we can predict how many moles of hydrogen we expect to form in the reaction. The molar ratio coefficient in front of the limiting reactant, sodium, is 2, and the molar ratio coefficient in front of the product of interest, hydrogen gas, is implied to be 1, and therefore is not written explicitly. These coefficients mean that for every 2 sodium atoms used, we will form 1 hydrogen molecule, or in other words, that we will make half as many hydrogen molecules as the number of sodium atoms that we start with. If we react 0.355 moles of sodium, we will form half as much, 0.355 divided by 2, or 0.178 moles of hydrogen. To convert this amount of hydrogen to the mass of hydrogen, we must multiply it by the molar mass of molecular hydrogen. Because there are 2 hydrogen atoms in a hydrogen molecule, this molar mass is 2 times the molar mass of hydrogen that can be found in the periodic table, 2 times 1.008 grams per mole, and that is 2.016 grams per mole. The mass of hydrogen that should form in the chemical reaction, in other words, the theoretical yield of hydrogen, is then 0.178 moles times 2.016 grams per mole, and that gives us 0.359 grams. The theoretical yield of hydrogen gas is 0.359 grams. However, the problem told us that the actual yield obtained in an experiment was 0.258 grams. The percent yield of hydrogen is therefore 0.258 grams divided by 0.359 grams times 100%, or 71.9%. One reason that the percent yield is considerably less than 100% may be that gases, and in particular hydrogen, are relatively hard to collect completely without allowing any to escape. Notice that in this problem, we could also calculate the theoretical yield of sodium hydroxide. The molar ratio coefficients in the chemical equation tell us that the number of moles of sodium hydroxide formed should be the same as the number of moles of the limiting reactant, sodium, that is used. If we have 0.355 moles of sodium, we should form 0.355 moles of sodium hydroxide. The molar mass of sodium hydroxide, calculated as the sum of the molar masses of sodium, oxygen, and hydrogen, is 39.997 grams per mole. Therefore, the mass of sodium hydroxide that should form the theoretical yield of sodium hydroxide is 0.355 moles times 39.997 grams per mole, and that gives us 14.2 grams. However, we can't calculate the percent yield of sodium hydroxide because we were not given the actual experimental yield of sodium hydroxide. One reason may be that the sodium hydroxide that formed is in aqueous solution dissolved in the water that remained unreacted, so determining its mass is not straightforward. The mass of the solution is the sum of the masses of the sodium hydroxide, which is the solute, and water, which is the solvent. And it's hard to determine how much of the mass is sodium hydroxide and how much of the mass is water. To determine the mass of the sodium hydroxide alone, one would need to remove the water and only then weigh the remaining solid. As you may remember, in the lab we have performed an experiment where sodium chloride table salt formed in aqueous solution as a result of the neutralization reaction between sodium hydroxide and hydrochloric acid. To weigh the salt that formed, we first had to evaporate the water.